So, to recap, little g is smallest at the equator, and the vertical and horizontal directions are indeed at right angles. But because of the centripetal acceleration, the Earth is not exactly spherical. Earth's diameters at 0 latitude are slightly larger than the diameter from pole to pole. Because the centripetal acceleration is very much smaller than g, the effect is very small. If the acceleration were larger than g, things would indeed be awkward. So, little g varies with latitude. It also varies with altitude. As we get further from the Earth, the gravitational force gets smaller as 1 on r squared. And so does the gravitational acceleration, little g. Now that raises a problem. Previously, we wrote potential energy, ugrav, equals mgh, assuming that little g was constant. Well, g is almost constant if we stay near the Earth's surface, but at large altitude, the attraction gets smaller, so the potential energy rises less quickly with altitude. Here is the expression for the gravitational potential energy of two masses, big M and little m, at separation r. And here's what it looks like using the Earth as an example for M1. Qualitatively, it makes sense. Close to the Earth, the attraction is strong, so we have to do lots of work to raise M2 a given distance. So the slope of potential energy versus altitude is large. Further away, weaker attraction, smaller slope. Remember that we have to define the zero of potential energy. Previously, we used floor level or ground level or whatever was convenient. For the astronomical version, we see that the potential energy goes to zero at very large separation. This makes sense. Astronomers want one reference that works for every planet, star, galaxy. Note that for astronomers, the potential energy is always negative. It takes work to pull planets and stars apart. Actually, going back to the beginning, astronomical bodies lost lots of potential energy when atoms came together to form stars, galaxies, and planets. Well, I hope you're thinking, how can we have two very different expressions for potential energy? The exact one is U equals minus G m1 m2 over r. And let's call the approximate one U dashed equals mgh. Remember that they have different references. The astronomers put U equals 0 a long, long way away, while we could put U dashed equals 0 at the Earth's surface. So both axes are different on our graph. Here is the linear approximation to the full expression. And these two are consistent, provided we stay very close to the Earth's surface.